Topic we are going to see minimal polynomial. First, we will see the definition of minimal polynomial. A least degree polynomial satisfied by a square matrix A is known as minimal polynomial. Now, this minimal polynomial is same as our characteristic polynomial. Now, how to find this minimal polynomial? For some matrix A, some square matrix A of order n, we will find out we will find out characteristic polynomial. We all know how to find characteristic polynomial. For given matrix A, characteristic polynomial is determinant of A minus lambda I. Okay. Now, after finding this polynomial, characteristic polynomial, if matrix is of order n, means matrix is a n by n matrix, then degree of this characteristic polynomial is n. In previous topic we have seen some examples of 2 by 2 matrix, 3 by 3 matrix. For 2 by 2 matrix, degree of characteristic polynomial is 2. For 3 by 3 matrix, degree of characteristic polynomial is 3. Okay. Now, there exists a unique minimal polynomial ma of lambda. Now, as characteristic polynomial, C is for characteristic polynomial of matrix A and variable lambda. Yes, similarly here minimal, so M of matrix A in variable lambda. Now there exists a unique minimal polynomial ma of lambda such that ma of A is 0, as Cayley-Hamilton theorem says that every square matrix satisfies its characteristic polynomial. Satisfies its characteristic polynomial means what? Instead of lambda we replace A, that is Ca of A, then it is 0. Satisfies means what? If we put A instead of lambda on the right hand side, characteristic polynomial gives us value 0. Similarly for minimal polynomial also, ma of A is 0. Okay. Now note that degree of minimal polynomial is always less than or equal to n. If matrix is of order 2 by 2, then degree of characteristic polynomial is obviously 2, and degree of minimal polynomial is less than or equal to 2, means either it will be of degree 1 or degree 2. We have to check this. Second thing, minimal polynomial always divides characteristic polynomial. Minimal polynomial is special case of characteristic polynomial. So minimal polynomial always divides characteristic polynomial. If lambda is eigenvalue of A, then minimal ma of lambda is also 0. Now this is important. Note that for matrix A, Ca of lambda is characteristic polynomial. After equating this characteristic polynomial with 0, we get some roots lambda 1, lambda 2. These are suppose 2 roots. Then these lambda 1 and lambda 2 are also roots of minimal polynomial, that is ma of lambda 1 and ma of lambda 2. Both are 0. Now we need this third thing time by time. Let us see one example. A is a 1 0 0 1. Here characteristic polynomial is determinant of A minus lambda I. So we can do the matrix subtraction. A minus lambda I as 1 minus lambda 0 0 1 minus lambda, and determinant of this matrix is obviously 1 minus lambda square. Now 1 minus lambda square and lambda minus 1 square both are same. So here we get lambda minus 1 square, which is nothing but lambda square minus 2 lambda plus 1. Now note that here degree is 2. Yes, here degree is 2, which is same as order of our matrix. Here order of matrix is 2, and degree of characteristic polynomial is also 2. Now we note that minimal polynomial say ma of lambda divides characteristic polynomial lambda. So possibilities are as follows. Now here minimal polynomial, there are three things. Minimal polynomial, degree of minimal polynomial should be less than or equal to 2. So either it will be 1 or 2. And minimal polynomial always divides characteristic polynomial. Yes, so possibilities for minimal polynomial are only two, either lambda minus 1 or lambda minus 1 square. But this lambda minus 1 square is nothing but our characteristic polynomial. Okay, now if lambda minus 1 is our minimal polynomial, then degree is obviously 1 because here power is 1. And if lambda minus 1 square is our minimal polynomial, then degree is 2, which is nothing but our characteristic polynomial. Now lambda minus 1, case 1, lambda minus 1 is minimal polynomial if and only if ma of a is 0. Now what is ma of a? Instead of lambda, here instead of lambda we put out a. So what will happen? So here instead of lambda, if I replace here by a, so here I will get a minus 1. Instead of 1 I will replace here I. Okay, here also instead of lambda, if I put it a, then I will get a minus I square. Now if this is our minimal polynomial, then ma of a has to be 0. Suppose ma of a for lambda minus 1 is non-zero, then obviously we will go to our case 2. Now let us check our case 1. Here ma of lambda is lambda minus 1, so ma of a is obviously a minus I. Now here a minus I is a, this is I, so this is 0. ma of a is 0, that is 0 matrix. So our minimal polynomial is our case 1. Yes. Now second case, minimal polynomial of lambda minus 1 square, c of lambda, ma of a is ca of a, that is remember a minus I square, which is obviously 0 because every matrix satisfies its characteristic polynomial. As we all know, ca of a is 0, and our for case 2 minimal polynomial is also same as characteristic polynomial. So here for case 2 minimal polynomial is ma of a is 0, which is of degree 2. Now note that there are two cases, there are two minimal polynomials, both satisfies ma of a is 0, but there is change in degree. Here for case 2 there is degree of minimal polynomial is 2, and here degree of minimal polynomial is 1, and all we know that a least degree polynomial is our minimal polynomial. A least degree polynomial among these two cases is our minimal polynomial. So obviously minimal polynomial is lambda minus 1, and this is our final answer. Here are some properties. Minimal polynomial of a always divides characteristic polynomial of a. By using this first property, we develop choices for our minimal polynomial. Depending on the degree of characteristic polynomial, there are many choices for minimal polynomial. If second property, if lambda is the root of minimal polynomial of a, if and only if lambda is a root of characteristic polynomial of a. If lambda is a root of minimal polynomial of a, if and only if lambda is the root of characteristic polynomial of a. Similar matrices have same minimal polynomial. Similar matrices, if there are similar matrices, we all know definition of similar matrices. If matrix B is similar to matrix A, then there exist P inverse AP is equal to B, where P is a non-singular invertible matrix. But here note that converse is not true. Okay. Now here we will see one example. Suppose A is a matrix of order 4 by 4 and characteristic polynomial is lambda minus 2 square, lambda minus 1, lambda minus 3. Okay. Now here cases. The main important thing is cases for minimal polynomial. Cases for minimal polynomial. Cases. Case 1, minimal polynomial. Now while formatting cases, we should note our properties, that what we all know, minimal polynomial always divides characteristic polynomial. Yes, minimal polynomial always divides characteristic polynomial. And what is the second thing? If lambda is root of characteristic polynomial, then lambda is also root for minimal polynomial. Yes. Now here for our characteristic polynomial, the roots are lambda 1 equal to 2, which is twice 2, because lambda minus 2 square is 0. So here it is 2 times 1 and 3. Now while making cases, we should note that the term lambda minus 2, lambda minus 1 and lambda minus 3 should be always there. Yes. So now let us make cases. This is our case 1. As we all know, we should minimal polynomial is a least degree polynomial, so we will start from lower case. The lower case means here first case should be lambda minus 2 into lambda minus 1 into lambda minus 3. Now note that one can also say that if I write down only these two terms, lambda minus 2 and lambda minus 1, if I not write lambda minus 3. But this is not true, because as we all know, lambda is a root of characteristic polynomial, then lambda is also root of minimal polynomial. So here 3 is a root of our characteristic polynomial. But for this first case, 3 is a not root of our first case. So as it is a root, so there should be term of lambda minus 3. Now we will make some combination of their powers. Now here what we have now, we should have all these terms, lambda minus 1 and lambda minus 3. We should have all these terms. If I see at our characteristic polynomial, the order of lambda minus 2 is 2, here it is 1, here it is 1. So only possibility for our next case is this only, lambda minus 2 square, lambda minus 1 and lambda minus 3. These are only two cases. Now note that this is nothing but our characteristic polynomial. So as this is nothing but characteristic polynomial, and CA of A is 0 by Cayley-Hamilton theorem. So here for case 2, MA of A is always 0. So we have to only check our first case. For first case, if MA of A, that is A minus 2i into A minus I into A minus 3i, if this matrix multiplication is 0, then this will be our minimal polynomial. If this is not 0, then obviously the minimal polynomial will be this. Yes. Another example, suppose for some matrix A, lambda minus 2 cube lambda minus 3 square is a minimal polynomial. Now here obviously matrix is of order 5. This is 3, this is 2, so 3 plus 2 is 5, so order is 5. Now for this, how many cases are there? Now here 2 and 3 are the roots of characteristic polynomial. So term lambda minus 2 and lambda minus 3 always should be there. Now first case minimal polynomial is lambda minus 2 lambda minus 3. Our second case is these two terms are always there, lambda minus 2 lambda minus 3, these two terms are always there, the change is in only their powers. Now here I can take this term lambda minus 2 square lambda minus 3. Here for lambda minus 2 there are 3 terms, for lambda minus 3 there are 2 terms. At a time I will change only lambda minus 2. Now the second case is lambda minus 2 cube lambda minus 3. Now secondly, now I can't take here lambda minus 2 raised to 4. This is not possible because minimal polynomial is a least degree polynomial and it should be divide characteristic polynomial. Yes. So as minimal polynomial divides characteristic polynomial, minimal polynomial divides characteristic polynomial, it should be less than this. Now less than means what? 4 divides 8. 4 is less than 8. Similarly here minimal polynomial terms in minimal polynomial or powers in minimal polynomial should be less than characteristic polynomial. Now this is our first case, this is our second case, this is our third case. Now the fourth case. So here I can take lambda minus 2 and lambda minus 3 square. Similarly lambda minus 2 square, lambda minus 3 square. Similarly I can take lambda minus 2 cube, lambda minus 3 square. These are totally 6 cases. Now for each case you have to check, which one is 0. Yes, which one is 0. Now while checking, and this is your homework, first check this case. If ma of a for this matrix is 0, then this is our minimal problem, because here degree is 2, where degree of characteristic polynomial is 5. Our degree of minimal polynomial should be less than or equal to 5. This is of degree 2, this is of degree 3, this is of degree 4, this is of degree 3. How are doing 3? Here it is 1, here it is 2. 1 plus 2 is 3. Here 3, here 1 is 4. Here 2, here 1 is 3. 2 plus 2, 4. 3 plus 2, 5. Now this is nothing but our characteristic polynomial. So this is always 0 by Cayley-Hamilton theorem. So we will check for this. If this is not true, then I will check for this. I will check for this. Okay. So this is your homework. You have to do this. Now we will see some problems. How to solve exactly minimal polynomial. Let us see.